Okay, so this lecture is going to discuss programming and motion paths. Alright, so our objectives, the first thing we're going to do is talk about some simulation program and then discuss various methods of programming, talk about motion control paths, and then we're going to finish up specifically talking about Fanuc motion instructions. So simulation programs are programs that allow the robot to be programmed and tested before they're actually run on the real robot. RoboGuide is Fanuc simulation and virtualization software, and it's only available on Windows. There's also other programs out there that are available. Okay. So when we first started with robots back in the 50s up to the mid 70s, the functionality of the robots was purely repetitive, and the programming was basically done with mechanical stops and limit switches. Starting in the mid 70s, they started using standard programming languages. And they still do to this day. But the third generation also is increasingly using AI or artificial intelligence methods. They also use more sensors, including vision, camera systems to determine where the part is and whether the part's good or bad. Okay. All right, so when we're trying to instruct the robot on where to go, we need to do path control. And so path control is defined as the method that the controller uses to move the tool center point. Remember, it's really all about that tool center point, where the work point of the tool is at. And we will need to move it from point to point, and of course it can only move within the work envelope. So we're going to program points into the robot. These are sometimes referred to as translations or position points or simply points. There's four methods of path control. The first is what we call stop to stop, or sometimes referred to as pick and place. So you're usually just going to a few points, and so very limited instruction. Then we have point to point, which can either be through what we call natural movement or controlled. And then we have continuous. Okay, stop to stop, as I said, is pick and place. Is very limited sequence control. It's really the first type using limit switches and mechanical stops that we talked about. That was primarily first generation type robots. Okay, but some modern robots that don't need to be too complex can also use it. Okay, so the actuators are driven until they reach a mechanical stop or a limit switch. It's either on or off, and usually the motion is just moving in one direction at a time. PLCs can be used for this to actually do the control. So the PLC just senses the limit switch, status of limit switches, and sends on-off control to the actuators. Okay. Another method is stepper motors, where every pulse you send to the motor moves it so many degrees, and so you can count how many pulses you want it to move to control how far it actually moves. Okay. This is considered, stop to stop is considered open loop type control. There's no real feedback to the controller on the position or the velocity. So we send it out and it moves, but we don't have any monitoring of any kind of disturbance or anything that's happening until the limit switches or whatever has been tripped. So the next is point to point. And point to point, we're going to use, in this case, we're going to use something like the teach pendant that we discussed earlier. The stop to stop, a lot of times, is really just more hardwired sometimes and doesn't actually um, need to be taught so much. But with point to point now, we're going to teach the robot what points we want it to go to. So we use either a teach pendant or some other method, simulation software or whatever. We can also program it in there. But we're going to program in where the TCP point is going to move. And we can do that using either joint instructions and just tell it move this joint so many degrees, move this joint so many degrees, or we can use the world and or user frames. All right, so each location of a recorded point is going to be stored within the controller's memory. And so we have to store the location of all 6 axes. So we can either store the joints, J1, J2, J3, J4. We can store the angle of each joint, or we can store an XYZ, yaw, pitch, and roll value. Remember, technically these are all based on that tool center point. So we first have to teach the robot where the center point of the attached tool is at. And then all these points are based on that tool frame or reference frame. Okay. Now, one type of point to point is what I kind of term here natural movement. So if you think of your moving your arm or parts of your body, when you move them and you just are going to go from one place to the other to pick something up, we don't really think about it, but when we do that, our body naturally wants to move in a curved sort of line. So what you see here is the black line is showing the path when we programmed it, and maybe we programmed point 1 and then we jogged the robot over to the next point, and it maybe we moved it in a straight line, but then we told it to just remember that next point. And so when we do that, just because we jogged it over there in a straight line doesn't mean that it's going to move in that way. It's actually going to move in a much more natural path. And so the path that it's going to take is kind of just illustrated here as the red line, which is not necessarily the shortest distance between the 2 points that it's moving to. Also make a note that if you are changing the speed of the robot, the actual path that it takes may change also. Okay. Now this natural movement is easier for the robot to make the move, and it's easier program-wise in the software to get the movement smooth and to move there. So each servo, again, this is a more advanced controller here, so it's each servo has to provide feedback to the controller on its speed and position. So when it's going to move between those 2 points, and the controller basically knows what path that it's going to make, but the programmer doesn't know that. So that's handled by that base application software. Okay. All right. So here's an example, just kind of showing you we're moving from point A to point B, and we have the program path, and the robot is going to be moving in an X, Y, and could be a Z direction also. All right. Now the point-to-point path is useful for a lot of different applications. Number one, when you're just trying to program the robot to get it to move to one point or another within the work envelope, and you don't care about the path that it's actually taking, then that's point-to-point control is the desired method, because it's simple, it's a more natural movement for the robot, which means less stress on the parts of the robot. And some actual applications for this is something like spot welding, drilling holes, palletizing. We don't really care how we're getting to the next point. All we're concerned about is that we get to the right location. Okay. All right, so the next one then, it's still point to point, but this one is with controlled, extra controlled capabilities. And so with this, we can actually make a perfectly straight line movement or a perfectly circular movement. Okay, so if you think about going from, say, one edge of this book to the other, and in just a natural movement, if you were to put your hands or put your fingertip on one edge of the book and move it over to the other, you wouldn't necessarily just move along the edge, even though that's technically the shortest distance is a straight line. But when we move our hands and stuff, we would not naturally move it straight down the edge of the book. So the original natural point to point that I was talking about a little bit ago is that just with, do yourself, take a book or a ruler or whatever, put your tip of your finger on one edge, put your tip of the finger on the other edge, or move it to the other edge, and you're going to notice that, without thinking about it, you're just going to move it, and your arm's going to go that way. And if you try to move it faster, your arm's going to move a different path. Okay? However, when we're doing the controlled point to point, now I'm saying I'm going to control my finger the entire time. So I'm going to go from this edge to this edge, and the whole time I'm going to be going in a straight line along the edge of the book. Okay, and so that's the controlled. Now what's so we have to, when you do that, even as a person doing that yourself, you have to think more and concentrate that you're moving your finger and keeping it along that edge the entire time. The other aspect of that is that what these robots can do is not only are they going to maintain their fingertip along there, is they're going to move at a constant speed that entire time. And so, when you're moving along there, there's certain points where maybe your hand gets bent up or whatever, and it's a little bit harder to move it. And so just think about that, trying to not only keep your finger on that edge the entire time as it goes from corner to corner, but to move it at a constant speed the entire time. Okay. Or another thing, what we might say is, I want to move from here to there along that edge in a straight line, but I want to get there in 5 seconds. All right, so I'm going to move at a constant rate so that it's going to take 5 seconds to move that far, or maybe 30 seconds to move that far. And so that's some of the things that these controllers can do. And we'll see that when we get to the Fanuc motion instructions. Alright, so with the controlled path, we can do a linear move, which would be a straight line, or we could also do a circular move and make a complete straight circle. And I'm showing some examples there, but we'll discuss those a little bit later here. All right. All right. So this slide is just kind of illustrating that we're going from points 1, 2, 3 to 4, and as we move along here, when we're jogging the robot, we don't have to jog the robot directly to point 2 in a straight line. We could take some kind of curved line or whatever, but we're going to teach the robot to go from point 1 to point 2 to point 3 and then to point 4. And we're going to tell it then, when you do this in automatic mode, you need to do it in a perfectly straight line and maintain a constant speed and those sorts of things. So it doesn't matter. We're just teaching it those 4 points, 1, 2, 3, 4. But, so when we move the robot there, it doesn't matter how we got it to point 2 or point 3. But when it runs, we're going to tell it needs to run in a perfectly straight line. Okay. So some applications for these are for something like continuous arc welding. This is one of the things that robots do very well, because when you're arc welding, you need to move in a constant, consistent manner at a constant, consistent speed to get a very good arc. And another option or another application would be like mechanical assembly. Okay. All right, and the final one is a point to point, but it's an extension of that called continuous path. All right, so basically, if you think back in math class when you were drawing graphs or something, they probably kind of mentioned, right, that a line is essentially made up of a whole bunch of points. And so that's what the idea of this continuous path is the fact that we want the robot to move in some particular line. I mean, it doesn't have to be a straight line, but we just want to have it follow some path. And the path could be very curved in all 3 directions and things like that. And so what we have to do then is we have to basically just teach it hundreds or even thousands of points. So we have to have the robot remember these many, many points as it goes through there. All right, and so every few seconds you would have to have it, or maybe even milliseconds, you would have to have it moving to a separate point within there. Okay. All right. The downside of continuous path is that they use a lot of memory, because you're storing lots and lots of points. Okay, and you got to have very good control with closed loop and servo. We actually need that also with just the controlled point to point that we discussed before. It's got a very, very good control. And one application of this would be like spray painting, say, the body of a car, and you need to maintain the same distance even though the curvature of the car varies. And there's a link there at the bottom of a spray painting application that you can click on and watch. Alright, so now we're going to talk specifically about motion instructions for the Fanuc robot. And so we really kind of talked about a lot of this, but we're going to see how it's laid out. And ABB and Motorman and other robots have a very similar sort of setup, but we're going to just address the Fanuc instructions for this class. So the motion instruction is a programmable command, okay, or they actually with Fanuc they actually refer to lines within a program as instructions. So that's why, you know, I have motion instruction here. Okay, so the instruction is a command telling the robot where to move. Okay, and again, it's the tool center point that is the focal point of where it's going to move. I mean, the whole arm is moving, but what the software of the robot is concentrating on is where it's moving and how it's moving the tool center point. Alright, so the motion instruction is made up of 5 parts for Fanuc robots here. The first part is simply the motion type, and then the position or the point translation that we're going to move to, the speed that we're going to move, and the termination, which is, you know, what do we do when we get there? And then the 5th part is an option that you can add on. So, you know, so you don't need the option, but so you may only have 4 parts in the instruction. All right, so here's a simple motion instruction. It's got the 5 parts, but in this case, option is just a generic word sitting there to show that. All right, so here this slide kind of points out the motion type. So you see the first arrow at the bottom there on the left says motion type. And so the motion type can be either joint, which is that natural movement, the first point to point we talked about. That would be the joint movement, or the controlled point to point that we discussed, which is either linear, meaning it's going to move in a perfectly straight line, or circular. Okay, the top arrow there pointing to the P, that is the positional information, which is either a point position, or for Fanuc robots they have what they call position registers, which are points that are stored in these registers or variables that can be used by multiple programs. So points are unique to the one program that it's in, but if it says PR there, then it's actually using a position register, which is available to all programs in there. And so you have your point, and then the points have numbers, and then we can also add labels to those. But the square brackets with the 1 inside is simply saying that's point 1. So that's really all kind of part of it. The next is the speed. Okay, if you're in joint mode, the speed is basically a percentage of full speed of the robot. Okay, so if you remember, we talked about the LRmate 200IC robot, the one of the models that we have in the classroom. They can go 4,000 millimeters per second. That's the maximum speed that robot can move the tool center point. So if you use this instruction here and it has a speed of 50%, then what that's saying is that 50% would be 2,000 millimeters per second. Okay, because the maximum speed would be 4,000, so 50% is half of that. Now, that is the maximum speed when the robot is set to 100% speed. Remember that the teach pendant also has a little speed plus minus percent buttons on it, so we can change the overall speed. So if we were to reduce the speed of the robot down to say 10%, then when we ran this program in auto mode, it would be 50% of that 10%, which would be 200 millimeters per second. Okay. Then we have the termination. Okay, and the two types of termination here is fine and continuous. Okay, now fine, what that means is that when it gets this instruction says move to point 1 at a speed of 50% max speed, and then the termination says when you get there, stop. So the word fine means that's like final, finish, and so when it gets there, it's actually going to stop. Okay. And then the option, here in this case we have an acceleration option, which says accelerate at 100%. Okay, so this, the thing is, I did say that, when you're moving, it's moving in a constant, at a constant speed. Well, that's not quite true, because if it starts from a stopped position and it's got to stop when it gets there, it also has to accelerate up to that constant speed and then decelerate back. And what this acceleration option allows us to do is basically say accelerate faster or accelerate slower. In this case, it simply says accelerate at 100%, which is the default. So it's doing nothing. But we could say accelerate at, say, 10% instead of 100. And then that means that it's going to accelerate slower, so it'll take it longer till it reaches that set speed that we told it over here. We can also do various things like give it offsets, or if we have, say, a welding tip, we could say, hey, when you get to that point, do a weld, a spot weld, and then, then the next instruction would be move somewhere else. All right, so this is just showing you the motion type here. Up here in red, we see the J is the joint, and the joint, and this gray box is what it looks like on the teach pendant. When you're programming this, you'll see 3 options for the joint type: joint, linear, and circular. Depending on what kind of software you have on your Fanuc robot, you may actually have a couple of other motion types listed there. Okay. And again, the joint movement is going to be a curved move. It will not move in a straight line. It'll always have some kind of arc to it, and the amount of arc that it has may change depending on the speed of the robot. Okay, so one of the things we got to remember there is, since we don't really know what that path is, because as we speed up the robot or slow down the robot, that path may change. So when you're testing the robot, remember that when you're in teach mode, the robot can only move that tool center point 250 millimeters per second. All right, so so when we're testing it in teach mode, the robot may move along and move around an object or something and not touch that object. However, when you put it in auto mode and then maybe you test it again and it's still not hitting some object that's there, but when you run it up to full speed, it may actually run into that object because it's not following the same path. Okay, so you always need to be very careful when testing, and you want to kind of test in teach mode, of course, and then test with the robot at low speed just to test it and make sure everything's working, and then speed it up a little bit and then speed it up a little bit more until you reach full speed. On the other hand, if we do a motion type of linear, we're saying it's going to move in a perfectly straight line. Okay. Right. The circular motion actually gives you a partial circular arc shape. All right. Now, if you've ever tried to draw a circle, which I assume most of you have, um, if you're going to draw a circle on a piece of paper, you first actually have to take your pen and put it on the paper at the point you want to start to circle. So when you see this slide here, it's showing point 1, point 2, and point 3. Point 1 is the start point. That's where you had to get that pencil onto the paper. And that's not part of the circular movement because you got there some other way. You weren't going in a circular movement. So you notice here line 1 is actually shown as a joint movement to get me to point 1. But then the circular movement then is going to take 2 points, point 2 and point 3, which are point 2 is a point on the arc about halfway, and then point 3 is the finish point of that arc. So if you wanted to do a full circle, you would actually still have to use either a joint or linear move to get to where the circle is going to start. Then you would have to do a circular move with points 2 and 3, which would take you halfway around a circle. And then you would have to do another circular move to point 4, which would be 3/4 of the way around the circle. And then back to point 1, which would finish the circle. All right, so these circular movements, again, we can move both linear and circular movements. We can tell it to move at a constant speed of 100 millimeters per second up to, depending on the speed of the robot, 2,000 or maybe even 4,000 millimeters per second. Okay. All right, so when you look at that, some of the options for this is millimeters per second, centimeters per second, okay, for the speed, or inches per second. The other thing is we could say time, as I mentioned before, and I can say I want you to move through this circular movement, but I want you to take 10 seconds to go from point 1, which is where we started at, on the other slide at least, to point 3. So I'm telling it how long I want it to take to get to that point. Okay. All right, so I already kind of discussed this. We can see the gray box is just showing us what it looks like here. If you go to the point and choose, it actually says choice there. You press F4 and you get a choice of either point or position register. Okay, and I already mentioned all that. So one thing to say about these points or positions is the fact that they are stored. They can either be stored as the joints. So if you have a 6-axis robot, you just store the angle of each joint, and that's where you're going to go to. Or you can store the frame. So if you're in frame mode, it'll actually have a user frame and that tool frame that with that tool center point, both are stored as part of the point. Okay. All right. So the speed here, the third element in the motion instruction is the speed. And so depending on which of the joint types or of the motion types you choose, you have different options for speed. So you see with joint, you have either percent of full speed, or you can say take 2 seconds to get to that point, or take 5 milliseconds to get to that point. Now remember, there is a maximum speed on the robot. So if you tell it you want it to go from 0.1 to 0.2, which is, a meter away, and you tell it, you want it to get there in 1 millisecond, that's like 1,000 meters per second. So if your robot can't do that speed, then obviously it won't, and it won't let you do that. But as long as when you select either seconds or milliseconds, as long as it can reach that point within the time allotted, it will do that. Okay. But so we see with joint, you only have the three choices: either percent overall speed of the robot, or take this many seconds to get there, or take this many milliseconds to get there. With linear or circular, we can tell it to move so many millimeters per second, or centimeters per inch, or excuse me, centimeters per minute, or inches per minute, or we can do degrees per second, seconds, or milliseconds. Okay, which the seconds and the milliseconds is an option for all three types. All right, so the termination, I already kind of discussed that. Fine means that we're going to stop when we get there. So we have to, we're going to be speeding up to whatever speed that it's going to take, that we're going to move. And then when we start getting close, we know we have to stop. So we're actually going to have to decelerate back so we can stop. Okay. So fine means that we're going to stop. However, continuous means that we're not going to stop at that point. And so you can see here, you can do a continuous 100, continuous 50, continuous 0, and you actually can pick any number between 0 and 100 for continuous. But what the continuous says is what we're going to do is we want to kind of get to point 2, but we don't care if we actually touch point 2. And so if we're at continuous 100, we're basically saying, hey, our real goal is to get to point 3 or beyond. And so we're going to kind of head off toward point 2. But when we start getting, as we start narrowing it, we're going to start looking ahead to the next motion instruction and plan our path to get to the next motion instruction. And so we may just cruise right on past and never actually, we're not, the continuous says we are not going to stop at point 2. All right, so we're going to kind of head toward it for a while, but we're also thinking ahead that eventually we want to head off to point 3. And so if we're doing a continuous 100, we're not even going to slow down near point 2. We're just going to cruise on by and kind of wave as we go along. If we do a continuous 50, it basically says we're going to slow down to about half of our speed, but then cruise on by and start heading off toward point 3. Continuous 0 means that we're pretty much going to get to point 2, but we're not going to actually stop there. So we're just going to kind of slide on by, but we're going to be pretty close to it as we go by. All right, so the fifth element there, as I already previously mentioned, is the option. Okay, and we can do things like spot weld, accelerate, we can do offsets, we can skip to a label, which means skip into another part of the program. And there's actually lots and lots of options that are available here. This is just given a few ideas of what we can do. All right, now one thing, when you store a position point, remember that what you're storing is where the tool center point is. However, the problem with that is how do you get to that? So if you think about moving your arm over here to pick something up, like here's a screwdriver here. If I'm going to come over here and pick this up, all right, I'm kind of showing that I'm coming up from on top and I'm going to grab this and move it. However, if you think about my fingers being the tool center point right in between my finger and thumb here, I can actually also come in from the side. I can come in from this side, or I can come in from this side, or I could actually come from underneath and come up. Okay, and so what we're storing, that point, is this point here that I want to get to with my tool center point. So I want to bring my finger gripper here and grab at this point. However, the way I can get there, I can, come from one side, come from the front, come from the back. I can come from any angle or any direction. So how does the robot know how it's supposed to come in? And the answer to that is this configuration. Okay, so the configuration stores whether your what the shape of your arm is. So if I go to the next slide here, maybe it'll illustrate it a little bit better. So you see here with your axes, axis 5 is like flip or no flip. So if you're coming down from the top, that would be a no flip. If you're coming from underneath, that would be flipped. If you look at the next one there to the right, you can see it's showing here your joint or axis A2. Axis A2, it can be kind of up and coming over and down, and so that would be down, or it could be bent way low and coming up from underneath. Okay. Another option is that it could be totally flipped over on its back. And so if we go back here and we see that we can be either flipped or not flipped. We can be either up or down, or we can be T for front, using the T at the end of front, or B for back. So this configuration here, when you store a point as a Cartesian point with XYZ, yaw, pitch, and roll, you store the user frame. You see UF there means user frame, and then UT means tool frame. Okay, it actually almost looks like a V, but it's supposed to be a U there. It's just the font they're using. But UT is user tool, UF is user frame. All right, so you have to store the frame of reference, and you have to store this configuration so it knows how to get to that point. So when you store points, you also have to store that configuration. So when we store the information, as I said, we can store it as a Cartesian point, XYZ, yaw, pitch, and roll, which stores the user frame, the tool frame, and this configuration. Or, as I mentioned before, you can just store, you've got 6 axes, they're rotational axes, so you can store just the joint position. What angle is this joint supposed to be at? All right, so if you store the points as joints, you never run into that singularity type of issue that we mentioned before. Okay. All right, so that's all for today.